Can you see the screen?
Yes, sir.
Okay. So this is what we have done in the last class. That in the last class we actually learned about S block and P block elements. Right? We had learned about this S and the P block element in our last class. Is this your note? So today we are going to see more about the periodic table. So now tell me, which one is the shortest period? Which one do you think is the shortest period? It's a future type of question. Which one is the shortest period? Tell me, which one do you think is the shortest period? It must be your period. Yes, sir.
Sir, period first.
Yes. The first period is your shortest period. So the shortest period is the first period because it has only two elements, hydrogen and helium. First period having only hydrogen and helium. Now tell me which one is the longest period? Which one is the longest period? Which one is the longest period? Solve the periodic table and tell me which one is the longest period. Which one do you think is the longest? So tell me. And tell.
Sir, 6.
Okay, yes, period 6 is the longest period. How many elements is there in period 6? Tell me, so let me see whether I can say it correct or not. How many elements are there in period 6? Period 6 has a total of 32 elements. Period 6 has a total of 32 elements. Why 32? Because you need to count even the lanthanides also. Because after lanthanide, you have the lanthanide series having 14 elements each. So that's why period 6 has 32 elements and hence it is the longest period. Sixth period is the longest with 32 elements. 32. And if anyone is asking about the incomplete period, then it is going to be the seventh, because there is still some element, the period 7, which is yet undiscovered. Period 7 is the incomplete period. Okay. Then tell me, what is the typical element? Any idea about typical element? What do we mean by typical element? What is a typical element? What do you mean by typical elements? See, elements of period 3 are called the typical elements. So the elements, element, period 3, elements in period 3 are called typical elements. So the elements that are present in period 3 are called the typical elements. Now why is it so? This is because they exhibit, they exhibit, they exhibit all the general properties, all the general properties all the general properties of the all the properties of the group, all the basic chemical properties that is there in the group is exhibited by elements of period 3. So that is why elements that are present in period 3 are called the typical element. Now you have the representative and normal element. What are that? Representative, representative or the normal element. Representative or the normal element. Representative or the normal element. Now what are they? So you see, S block and P block elements together are known as the normal element. S block, S block and P block elements except group 18. So what are the groups present in representative element? So that is group number 1, 2, 13, 14, 15, 16, 17. Group 18 can't be counted, it cannot be counted. So elements that are present in this group are called the representative or the normal element. So the typical element are the elements that are present in period 3, whereas the elements that are present in group 1, 2, 13, 14, 15, 16, 17, these are known as the representative or the normal element. That's just basic GK type definitions that you need to know. Now let's move on to the next part, which is as we are saying about S block, P block, D block, F block. So what do they exactly mean? What do you mean by an S block element? Or what do you mean by a P block element? So let's see. But before I say that, I hope you have done the electronic configuration. Are you all well practiced with the electronic configuration? Yes or no? Have you practiced the electronic configurations?
Yes, sir.
Okay, because we'll be needing them here. That's why you need to practice the electronic configuration. If not, otherwise it will be a problem to quickly catch up what we are writing and how we are writing. How much we have practiced. The S block element. S block element. We'll be studying about S block element. So who are called S block element? You see in the periodic table, what did I write? Group 1 and group 2. Element present in group 1 and group 2 together are called the S block element. So group 1, group 1 and the S block element. Okay. So let us write down the few configurations of group 1 and group 2 elements. Configuration of the elements of group 1 and group 2. So let's what are the elements present in group 1? Lithium, sodium, potassium. Just writing few. And so, what is the configuration of lithium? Lithium is helium 2s1, helium 2s1. Sodium is neon 3s1. Potassium is argon 4s1. So this is for group 1. Again, if you consider for the group 2, there you are going to see, suppose beryllium and magnesium, or you can have, it's like that is beryllium, magnesium, calcium. Beryllium is helium 2s2, magnesium is neon 3s2, calcium is argon 4s2. So you see one thing, that is elements in the same group. If an element is in the same group, then their electronic configuration will look similar. See, see the group 1, in all the cases, the electrons, it looks similar. 2s1, 3s1, 4s1, that means one electron in the valence shell, and that electron is present in the s orbital. You see all this configuration of group 1, the last electron has entered the s orbit, be it 2s1 or 3s1, 4s1, like this way. The last electron has entered the s orbit. Even if I write rubidium over here, it will be krypton 5s. So the configurations is similar. It looks similar down the road. Here we are getting to see that the last electrons enter the s orbit. Similarly, for group 2 also, the last electrons enter the s orbit. 2s2, 3s2, 4s2. The last electrons are entering the orbital. So it is said that the general configuration, that is, if we just generalize the situation, the general configuration is going to be NS, NS 1 or 2, 1 or NS1 or 2. So you see that since in this particular cases, that is in group 1 and group 2, since the last electrons enter the s orbital, that is why group 1 and group 2 elements are called the s block element. Since for group 1 and group 2, the last electron entered the s orbital, that's why group 1 and group 2 elements are called the s block element. Okay. And what is the generalized configuration? The general configuration will be NS. If it is for group 1, it will be NS1. And if it is in group 2, it is going to be NS2. So that is why if you combine them, it can be NS either 1 or 2. There can be either 1 electron present in the last shell, or there can be 2 electrons present in the valence shell. That's why NS either 1 or 2. And what is N? N is the number of periods. N is the number of periods. Okay. So is the concept of S block element, how we are getting them, clear to everyone? Is the concept of S block element clear to everyone?
Yes, sir.
Over here, the electrons, the last electrons, the valence electrons are entering the s orbit. That is why we call the group 1 and group 2 as S block element. Okay, so what about the others? How many are doing the class?
Sir, 2, sir.
Okay. So what about the other? Who is that? Is it Papia or uh, who is the other student? Can you let me know his name? Can you hear me? Hello? Yeah.
Yes, sir.
You too can hear. What is your name? You are Ayush. Or Abhay.
Ayush, sir.
You are Ayush. Who is the other one?
Other one is Nanika.
Nanika. Nanika, can you hear me? I don't think she can hear me. Then you have the P block element. So once you have done the S block element, then let's see the P block element. So again, you got the concept. So the concept will be similar. So here also you will see that the valence electron will enter the p orbit. That is why they are called p block elements. So let's see p block element. P block element. P block element. Block elements. See the periodic table. What are p block elements? That is group 13, 14, 15, 16, 17, and 18. These six groups are together called the p block elements. That is why let's write it. That group 13, group 13 to group 18 is the P block element. Group 13 to group 18 is our P block element. So let's write down the configuration of the P block element. See, let's see the period 2. What are the elements of group 13 in period 2? It is basically boron. After boron, you have carbon. Then you have nitrogen. Then you have oxygen. Then fluorine. Then neon. So if you see the configuration, it will be helium 2s2 to be 1. Carbon is going to be helium 2s2. Nitrogen will be helium 2s2. Helium 2s2. 4. Helium 2s2. 5. We have already done this configurations in atomic structure. Yeah, 2s2. Again, if you see for period 3, that is aluminium, silicon, phosphorus, sulfur, chlorine, argon. Aluminium, silicon, phosphorus, sulfur, chlorine, argon. So see the configuration here. It will be neon 3s2 51, neon 3s2 52, neon 3s2 53, neon 3s2 Fine. So from this configuration, you can see that in all the cases, the last electron entering the p orbital. That is, in all the cases, the last electron, that is the valence electron, is entering the orbital. So, sorry, in all the cases that you have written, in all the examples that you have written, from group 13 to group 18, the electron, the valence electron, is entering the p orbital. Hence, they are called the p block element. Okay. So, as all the electrons over here are entering the p orbital, hence they are called the p block element. And what is the general configuration? The general configuration is going to be general configuration in s orbital. Always two electrons are present: 3s2, 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 3s2. In all the cases, in the s orbital, always two electrons present. That is why ns, always two electrons are present in the s orbital over here. And np, the number of electrons in the p orbital, can range from 1 electron to 6 electrons. You see p1, p2, p3, p4, p5, p6. So the number of electrons in this p orbital can be anything in between 1 to 6. It can be either 1 or 2 or 3, 4, 5 or 6, whatever. So the value will be between 1 to 6. That is why thing is S2 NP 1 to 6. Okay, where N is the number of period. So since here we are getting that the electrons are entering, the valence electron are entering your p orbital. That is why they are called the p block element. And the general configuration of this element is NS2 NP 1 to 6. Okay, is it clear to you?
Yes, sir.
Then let's see about the d block element. And what about the d block element? So in d block element, the valence electron will enter the d orbital, and hence they are called the d block element. Let's see them. D block elements can be elements from group 3 to group 12 are together called the d block element. That means basically our transition metals are called the d block element. So let's see. Now we'll not write all the transition metals. We'll just write few examples of the transition metals so that we can understand the d block element thing. Let's take scandium. Let us take scandium. So what is the configuration of scandium? Scandium's configuration will be argon 4s2 4s2 1, argon 4s2 3d1. Okay. Then let's take titanium. Titanium, that is argon 4s2 3d. Then you see, let's take chromium, that is argon. This is an exception we have done in the last class. Argon 4s1 3d5. Then you have suppose copper, which is also another exception. Argon 4s1 3d10, and zinc will be argon 4s2 3d10. Over here, in all the cases, in all the 5 examples that I've written, the last electron enters the d orbital. In all the examples that has been written, the last electrons enter the d orbital. That is why they are called the d block element. So, what is the general configuration of this type of element? The general configuration will be, it will be as, in all the cases you have electrons in the 4s orbital. Either it is 4s1 or 4s2. So here you will write it as in this way: Ns 1 or 2. The number of electrons in the s orbital will be either 1 or 2. But yes, electrons must be present in the s orbital. And the number of electrons in the 3d orbital, that means with this respect it will be n minus 1. It was 4s. So 4 minus 1, that is equal to 3. 3d. So the number of electrons in the 3d orbital, or rather the d orbital, that is going to be in between 1 to 10. So in d also electrons must be there, and they will be in between 1 to 1 to 10. So in d orbital also the number of electron is going to be between 1 to 10. So this is the general configuration. Ns 1 to 2, because always electron must be present in this s orbital. So that is Ns 1 or 2. And n minus 1d, the value will range from 1 and it can continue till 10. Because see, for titanium we are getting 2 electrons in the d orbital. For vanadium there will be 3 electrons. That's why gradually if you see the configurations of atomic structure, that the electron numbers will be from Ns1 or 2 and n minus 1d 1 10. So this is the general configuration of the d block element. Okay, is it clear?
Yes, sir.
Yes, sir.
Okay. Who is this? Nalika.
Yes, sir.
Oh, you can hear me? Okay. Then let's see. See, we have heard about this thing called transition element. We have heard about transition element. So what is this transition element? I have already said that d block elements, you see the periodic table, that d block elements are only known as the transition element. Any idea what we mean by the transition element? Because you have learned it in lower classes. What are transition elements? Tell me. You remember? Do you remember the definition of transition element? What do you mean by transition element? Do you remember the definition?
Sir, elements with partially filled d orbital.
This is correct. This is correct. You read this in class 10?
No.
Then okay. The definition that is taught in class 10, that transition elements are those which have their properties in between highly metallic and highly non-metallic elements. So transition metals are those elements which have their properties in between highly metallic and highly non-metallic elements. So this is the class 10 level definition. But this definition is not a right one. Let's see the right definition of transition. That is the one that Nanik already told. But it's still not completely right. So these are those elements these are those elements which have vacant d orbital. Vacant d orbital. So this is the definition that Nainika told. That these are those elements which have vacant d orbital, or as you said, partially filled d orbital. So let's see what will be the problem if I take your definition as a correct. So let's see from iron. So what is the configuration of iron? Iron is argon, 4s2, 3d6, 3d6. So now tell me how many electrons can be present in the 3d orbital? How many total number of electrons can be present? What is the maximum number of electrons that can be present in a d orbital? In a d sub 10. So how many are over here? Here only 6 electrons. 6 electrons are there. So maximum number of 10 electrons can be present, but we are getting to see that only 6 electrons are there in the d orbital. So hence iron is a transition element. Because the definition is satisfied. These are those elements which have vacant d orbital. So that means you see for iron we are getting to see that there will be a total number, maximum number of 10 electrons can be fitted in the d orbital. Whereas we are just getting 6 electrons. That means there is a vacant orbital. We draw the box diagram also. You can feel that even better. 1, 4, 5. So you see 1, 5. Here, as you can see, that more 4 electrons can be fitted in the iron. So that means it has a partially filled or a vacant d orbital. Hence, iron is a transition element. Okay. Now let's see for copper. What is the electronic configuration of copper? That is argon, 4s1, 3d10. Argon, 4s1, 3d10. So d orbitals can hold a maximum number of 10 electrons. And for copper, we are getting copper has a 3d10 electron as a configuration of 3d10. So for copper, 10 electrons are already present in the d orbital. That means copper does not have any vacant orbital, vacant d orbital, because in d orbital, maximum number of 10 electrons can be fitted. Whereas in copper, we are getting to see that copper already has 10 electrons in the d orbital. So that means there is no vacancy in the d orbital. But what does the definition of transition element say? That we have vacant d orbital. So that means if this definition was completely correct, then according to this definition, copper would not have been a transition element. According to this particular definition, copper must not be a transition element because it does not have a vacant d orbital. Okay, so that's why I told Nainika that your definition is not completely correct, rather it is partially correct. There will be more addition to that particular definition. So now let's complete the definition. Nainika, did you get it where your definition is lagging?
Yes, sir.
Okay, so these are those elements which have vacant d orbital. Now you have to add to this that either in their ground state, either in their ground state. Ground state মানে এই যে এরকম normal state, this type of normal simple neutral state, either in their ground state or in any one of the stable oxidation state. Now this is a complete stable oxidation state. So you see for copper in ground state, copper has 10 electrons in the d orbital. Hence, if we just consider the ground state thing, then I will say that copper is not a transition element. But the moment I add the second line, that is or in any one of the stable oxidation, then there can be chances. Now, what are the valencies or what are the oxidation that copper can have? Copper can have either +1 or +2. Copper +1, copper +2. These are the two valencies of copper. So let's see the configuration for copper +1. Copper +1. That will be argon 3d10, because the electron will be eliminated out from 4s orbital. So the configuration will be argon 3d10. So here also you see for copper +1, here also there are 10 d electrons, no vacancy. But if we consider copper 2+, copper, then the configuration will become argon 3d9, argon 3d9. So now for copper 2+, you are getting to see that yes, there is a vacant d orbital in copper 2+. Because the d orbital can hold a maximum of 10 electrons, but copper 2+ has 9 electrons. So it is a partially filled d orbital. So that is why this complete definition is important. And see, it also says a stable oxidation state. So it doesn't be just for making your definition correct. You will take any oxidation state. You cannot take copper 4+, copper 6+ just in order to prove your point. You have to take only those oxidation states which is generally formed naturally, like copper +1 and copper +2. Other than this, no other oxidation state of copper exists. So only these two will be considered for taking the criteria of transition element. And also there is no such that both the oxidation state has to satisfy the condition. It says any one. So, okay. So anyone, if any one of them has a vacant d orbital, in copper plus 1, there is no vacancy in the d orbital. 10 d electrons are there. But for copper 2 plus, you are getting 9 electrons in the d orbital. So that's why anyone, if it is not here, but it is present in this particular oxygen. So that is why copper is a transition element. Okay, is this clear to everyone?
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
then let's see for zinc. So now what is the configuration of zinc? Zinc is argon, argon, 4s2, 4s2, 3d. Okay, so zinc is argon, 4s2, 3d10. So you see for ground state of zinc also, you are getting to see that there are 10 d electron. That means no vacancy in the d electron orbital. D orbital is completely free. So now let's see the second condition, that is in any one of the stable oxidation state. Now what can be the oxidation state of zinc? It is Zn. What is the valency of zinc generally? It is zinc 2 plus, Zn2 plus. See all the compounds of zinc that you have studied in lower classes, be it ZnSO4 or ZnCl2, whatever, they all are Zn2 plus. So zinc can have only one oxidation step, that is Zn2 plus. But even in Zn2 plus situation also you are getting argon 3d10. So even in this situation also you are getting to see that zinc has 10 electrons in the d orbital. That means even in Zn2 plus, d orbital is completely occupied. There is no vacancy in d orbital. You can say that zinc does not satisfy the definition of the transition elements. But zinc again has some of the chemical properties that is shown by a transition. So zinc, although it does not satisfy the basic definition of a transition element, yet it has some of similar chemical properties to that of a transition element. That is why when I had written the periodic table in the previous class, I have said that zinc, cadmium and mercury are borderline elements. That means they are somewhere in the border, they are somewhere in between. That is why zinc is said to be a borderline element. So since zinc does not satisfy the basic condition of your transition element, yet they have some similar chemical properties to that of the transition element. Hence, the group 12, that is zinc, cadmium and mercury, are called the borderline elements. Okay. So this is about the D block element and the transition element. The D block elements are only known as the transition element. Now let's see for the F block element. F block element. F block element. So what are the F block elements? F block element consists of the lanthanides, and the actinides. The F block element consists of lanthanides and actinides. Okay. So here also, as you can understand, that is for F block element, the last electron will enter the F orbital. The valence electrons will enter the F orbital. Hence, they are called the F block element. So lanthanoids and actinoids are together known as the inner transition element. These elements are called the inner transition element. Inner transition element. So if the question mentions inner transition elements, that means it is referring to the lanthanide and the N. Now, what is the general configuration? Now, as you know, the lanthanide and actinide's nomenclature, electronic configuration is not something that you have in your level. You just need to know the general electronic configuration. That will be enough. So, the general configuration of lanthanides will be this you need to memorize. General configuration, that is general configuration will be NS2, NS2, N minus 1, D, 0 to 1, N minus 2, F, 1 to 14. So this is the general configuration of the lanthanide. That is NS2, N minus 1D, 0 to 1, and N minus 2F, 1 to 14, where N is the number of well, I'm writing few configurations of the F block element. Although you do not need to know this configuration, these are just for the sake of understanding. I'm writing it down. So let's start with the configuration of cerium. Let's see the configuration of cerium. You do not need to know the configuration. This is just for the sake of understanding. So cerium will be the xenon 6s2. So yes, ns2 6s2. Okay. Then you see 5d1, 5d1, n minus 1, 6 minus 1, 5, d1. Then again n minus 2, that is 6 minus 2, that is equal to 4f. How many electrons in the 4f orbital? Only one electron. So you see it is satisfying this condition. 6s2, 5d1, 4f, 1. Then see for praseodymium. Then see here, praseodymium. The configuration for praseodymium is, what does it say? NS2, that means 6s2. Because it is present in the 6th period, so that is why 6s2. Then it will be, there are no d electrons. So you can write in this way 5d0. But there's no point of writing 5d0 because 0 electrons. So what's the point of even mentioning? We'll write 4f 3. 6s2, 4f 3. Then you have, suppose, gadolinium. Gadolinium, GD. 6s2, 5d1, 4f 7. So you see here also the condition is being satisfied. And in all the cases, the last electron is entering the F orbital. That is why they are called the F block element, as the last electron is entering the F orbital. Okay. Is it clear why we call them the F block element?
Yes, sir.
Yes, sir.
You need to remember the general configuration, and but not the configuration of this element, only general configuration, and understanding why you say them the F block element. Now see, now you can see one thing, that is previously, like, we had the names like very easy names: phosphorus, sulfur, silicon, or germanium, tin, lead. So these are metals which are quite easy names. And these are also metals which are very, very known to us. But as we're moving on towards the end of the periodic table, we are getting to see that the names of the element are becoming more and more complicated. For example, Gd is gadolinium, Pr is praseodymium, promethium. So the names are becoming so very complicated. And moreover, these elements are not even common to us. And that even makes it more difficult for us to remember, right? So what we're getting to see that is that as we're moving towards the end of the periodic table, just a minute, please wait for a minute. Okay, so yes, as we're getting to see is that as we're moving on towards the end of the periodic table, the names of the element are getting more and more complicated, and moreover, the elements are not that common. So we face a problem is that they are difficult to remember, so much complicated. Okay, so that is why we have started giving kind of scientific name, just like in organic we have done IUPAC nomenclature. So here also we have started to give a logical name to the elements with a very high atomic number. So now we are going to see the rules of naming these elements with a high atomic number. Although I say that the elements are like not uncommon to us, but let me just give you an example that no, they are quite useful also. See, the Gd, this gadolinium is extremely important. Do you know the use of gadolinium? I don't know whether you have trained in biology or not. Did you hear of this element called gadolinium before? Yes or no?
No, sir.
See? Okay, you have heard about MRI? MRI is like a kind of diagnosis, the magnetic resonance imaging that
Yes, sir.
doctors prescribe. So
Yes,
this
sir.
Yes, sir.
so this gadolinium is used as an imaging agent in MRI. Gadolinium is being used as an imaging agent in this MRI machine. So that's why gadolinium has like a huge medical application. MRI imaging agent, or you can also say at like a contrasting agent. Basically, imaging or a contrasting agent. That is the application of gadolinium medical field. Because although you do not have these things, because since gadolinium has 7 unpaired electrons, that is why it can produce such a strong image. Anyway, so the thing is, gadolinium is used in MRI. So that means in every hospitals, huge amounts of gadoliniums are being used. Anyways, so now we are going to see the IUPAC nomenclature, the rules for the IUPAC nomenclature. Now this is very easy thing. Is IUPAC nomenclature of super heavy elements. IUPAC. IUPAC nomenclature. IUPAC nomenclature of super heavy elements. IUPAC nomenclature of super heavy elements. That is Z greater than equal to 1. So let's get to see that how do we name this element which have an atomic number greater than 100. So if the atomic number of the element is greater than 100, then how are you going to name this element? So let's how do we name them? Do you know the full form of IUPAC? Do you know the full form of IUPAC? IUPAC's full form is This is International Union. International Union of Pure and Applied Chemistry. International Union of Pure and Applied Chemistry. So that is the full form of IUP. It's just general interest. Okay? Nothing for the examination important. It's like just a council, just like we have like United Nations, which has representatives from all the countries that are member of the uh, organization. So here also IUPAC is also an organization which has different scientists as a representative of their particular country. So and these standard rules are actually made by this governing body called IUPAC. It is IUPAC which makes all this convention of chemistry. Anyways, so let's see the IUPAC rule. It's very easy. The first rule is the rules you do not need to know. You do not need to know the rules for your examination purpose. No one is going to ask you to write down the rules. But all what you need to do is apply the rules. So there's no point of mugging up the rules. I am writing it down just so that you can understand. But there's no point of mugging up the rules. You just need to apply the rules and do the namings. That will be it. The thing will be, so the rule is the digits, let me write down the rules first. The digits expressing atomic number of element, atomic number of element is expressed as or is written as if it is 0, if the digit is 0, we say it nil. If the digit is 1, we call it un. If it is 2, then we call it pi. If it is 3, tri. Quad. Pent. Hex. Sept. Oct. 9 will be n. Okay, so this is how we are going to call the digits. Nil, un, bi, tri, quad, pent, hex, sept, oct, and n. And then the second point will be that is the roots are then put together. That means the letters and the digits are put together. The roots are then put together. The roots are then put together. And the name is terminated by iam. And the name terminated by ium. And the name is terminated by ium. Okay, so let's see an example. It will become more clearer to us. Suppose what if the it is atomic number is 1, 0, 4. Suppose if it is the atomic number 1, 0. So what is 1? 1 mane un. So we write un. Un. Then you have 0. 0 mane nil. Nil. So un-nil. Then 4 mane quad. Quad. Un-nil quad. And then the name is terminated by ium. So at the end we will add IU. So the name becomes un-nil quad ium. And what will be the symbol? The first letter of the digits. So un n q. So it will be n q. Is it clear to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
So it's very easy.
Yes.
Nothing. Just you have to remember these first letters and you have to do it. Very simple. Okay, so you do one. That is, suppose if it is 2, 2, 7. So what will be the name of this compound? If the atomic number, what is the name of an element which has an atomic number of 227? So you see the benefit of this rule is even if the element is not discovered, we can take any atomic number greater than 100 and we can apply the rule to that. What will be the name of this element? Tell
By,
me. Yes, by then.
by,
Yeah.
sep,
By then 7 mane sept,
Sept.
and then end with terminated by ium.
Em.
So at the end you add IUM plus that will be by septium. And the thing is BBS. The symbol will be BBS. You see that even though the names are looking complicated, but they're very easy. Yeah, and you do not even need to memorize them. Even though it looks such a complicated name, if you do not know the rules, that Anil Thwatia, that's a complicated name without knowing the rules. Once you know the set of rules, very simple. So this is how you are going to name them according to the IUPAC format. Now see, there are a third point to this particular. The third point will be that is going. In order to avoid repetition, in order to avoid repetition of some letter, in order to avoid the repetition of some letters, the following procedure may be adopted. The following procedure may be adopted. The following procedure may be adopted. So what will be the procedure? n plus n. Suppose if there is 9 followed by a 0, if you have to write it, it will become E N N N I N. That means 3n are coming. What's the point of writing 3n? The instead of writing 3n, it N N I N. We just remove one n from. Or suppose if the letter is by followed by ia. So if you have to write it, it will become. If you just simply add them up, it will be B I U M. Giving two I doesn't make any difference by like this. So it will be BI UM. That will be enough. I UM. Similarly, try RI and EM. That will be RIUM. Try. Okay. So quickly tell me what will be the name of 190. 190. If you do this, become 1 money un, 9 money n, but there is also a 0. So n and nil. So that means it will be 2n, n nil. E N N I N. So be careful with the spelling over here. And then you end it with ya. So un and nil ya. Or suppose if you get like suppose 1, 1 or 1, 2, 3. 1, 2, that is un by triumph. Un by triumph. So this is how you name the element. Okay. So with keeping the spelling in. So this symbol will be the symbol for the element will be U, E, and N. That's why U, E, N. U, V, V. So this is how you are going to name this particular element. Is it clear to everyone? Yes or no?
Yes, sir.
Completely
Yes,
clear.
sir.
Com- yes. Did anyone say something?
No.
No, sir.
Okay. So, okay. So this is very easy. This will come also in your exam. So might be there two will come, maybe 2 or 3 might come. So this over here, this is something that you cannot afford to make any mistake. And again, you do not need to know these rules. Mane, no one is going to ask you to write down the rules. You just need to apply and find out the name of the compound. Sorry, the name of the elements. Okay. I think that will be all for today. And then we'll be continuing with the chapter in the next class. That means tomorrow only. So in the next class, we'll be doing in fact the more conceptual thing. This was easy stuff today. From next Hello.
Yes, sir.
Yes, can you hear me?
Yes.
Yes, sir.
So I was asking that in the topics that has been taught today, do you have any other difficulties?
No, sir.
Okay. So then that's it for today. Then I'm disconnecting the call for today and we'll be meeting again tomorrow.